we're finishing up. It's pretty obvious I'm not going to be able to do everything on clustering that I wanted to do, but we'll probably do a little bit of it and then just declare victory, I think. At any rate, so what I gave you was an algorithm for this all pairs or drug interaction problem that gave you an upper bound on how many times do you have to replicate in order to have a small value of the reducer size. And if you want to have a theory of algorithms that works on MapReduce, I also have to talk about lower bounds. It's like, hey, quicksort is a way to sort in time n log n, but you also want to have you want to be a proof that says you can't sort in less than n log n time. Okay, so in our case we had R is at most 2D over Q. I would like to be able to say, well, R has to be at least 2D over Q. Well, it turns out that's not true. And in fact, you can make R as close, you can get rid of the factor of 2. R does have to be at least D over Q. And I want to prove that to you. And in the proof, I'm going to introduce this idea of a mapping schema and show how the existence of a mapping schema implies a lower bound on replication. Okay, so again, a mapping schema is a solution to a problem using a particular reducer size Q. Okay, and the two things you have to respect to have a mapping schema. Okay, first of all, what is a mapping schema? It assigns inputs to reducers. So each reducer is assigned to some set of reducers, maybe 1, maybe 2, or maybe 3,000. Or similarly, each reducer gets a set of inputs that are assigned to it. And the first constraint is the obvious one. It says no reducer can be assigned more than Q inputs. That's the definition of reducer size. But the second is a little bit subtle. It says that for every output, and remember there's an input-output mapping that describes the problem itself. So for every output, there's a reducer, at least one reducer that has all of the inputs that are related to that output. See, okay, so we'll say the reducer covers the output, and it should be obvious that if there's an output that isn't covered, then that output cannot be computed, because only a reducer can compute an output, and if no reducer has all the information that's necessary to compute the output, you're doomed. Okay. So again, my theory is that this is the existence of a mapping schema for every algorithm, every MapReduce algorithm is the constraint that parallel algorithms in general don't have. Okay, so let's look again at the drug interaction problem, and let's try to devise a lower bound. Again, we have reducer size Q, there are D drugs. Now I know that each drug has to meet the D minus 1 other drugs at some reducer, right? Okay, so if I send the drug to a reducer, then I can send at most Q minus 1 other drugs to that reducer, because I can send only Q drugs to any one reducer. So if I have to meet D minus 1 drugs and I can only meet Q minus 1 at any one reducer, how many reducers do I need? Well, it's at least the ceiling of D minus 1 over Q minus 1. And that says, well, that the replication rate has to be at least D minus 1 over Q minus 1. In this case, remember, R is actually just the average replication rate, the average number of copies of each input. But in this case, every input has to go to at least a ceiling of D minus 1 over Q minus 1. So at any rate, certainly the replication rate, let's call it d over q, forgetting about the minus ones and the ceiling and so on. So it says r is at least d over q. Remember, I have an algorithm that has r is equal to or less than 2d over q. So the lower bound is half what I described. So then the question is, what's wrong? Is my lower bound not strong enough, or is there a better algorithm? Well, it turns out that there is actually a better algorithm. Okay, and that you can get rid of that factor of 2, that r equals d over q plus 1 is achievable. Okay, I'm not going to go into that. It's, in fact, a complicated algorithm that nobody would bother to implement, but it does exist. Okay, so with that little introduction to the theory, I want to talk about another class of problems. And as I said, I've been working with my son Jonathan on this a little bit. And we call them sum pairs problems in the sense that instead of wanting all pairs of inputs to meet, I have some particular notion of which pairs of inputs need to meet. But each output is still associated with only 2 inputs. That's not a general problem. Like in matrix multiplication, each output is associated with a very large number of inputs. Anyway, what we have, I want to talk about the Hamming distance problem as an example of a realistic sum pairs problem. And well, then I'm going to tell you, there are 2 algorithms that will work in general and are kind of obvious. And the interesting thing, again, that my theoretically inclined son was able to do is to show that in fact, there's more or less nothing better than the obvious approaches in general, okay, which is not true. For some specific instances of a sum pairs problem, there are in fact much better algorithms and we know about them. But there's nothing general that works for all sum pairs problems. So again, using the same model of a problem, we'll say a problem is a sum pairs problem if the outputs are sum of the pairs of inputs. That is, each output consists of 2 inputs, and maybe all pairs are there, but probably just some of the pairs are there. So just as an example, I want to talk about HD1, or Hamming distance 1 problem, where inputs are bit strings of length b for some particular b. And the outputs are all pairs of inputs that are at Hamming distance 1, where the Hamming distance, I assume most people are familiar with this notion, but it's the number of bit strings, the Hamming distance between 2 bit strings is the number of positions in which those bit strings disagree. So the Hamming distance 1 problem is the outputs are all pairs of inputs that disagree in exactly 1 bit. Okay. Well, this is actually in the paper on the theory. This is one of the problems that we were actually able to analyze. And what you get is this. There's both an upper and lower bound. Is that the replication rate is b over log base 2 of q. So there's still this inverse relationship between the reducer size and the replication rate. The bigger the reducer size, the less the replication. But in this case, instead of it being a linear relationship, it's a logarithmic relationship. So r grows it almost doesn't matter. R is never very big. So here's an example. Well, for the case of bits of b equals 2, there's bit strings of length 2. There are 4 inputs. There are actually 4 outputs. Because of the 6 pairs of inputs, 4 of them are Hamming distance 1, like 0, 0 is obviously Hamming distance 1 from 0, 1. The only ones you don't get are the ones sort of at the corners of the square. 0, 0 is distance 2 from 1, 1, and 0, 1 is distance 2 from 1, 0. So they're not outputs. So this is why it's a sum pairs problem. Now, as I said, there are algorithms that match the lower bound that I gave you for a wide variety of values of Q. And so what I'd like to do though is say, is there some algorithm that works for any sum pairs problem and takes the advantage it can of the fact that not all pairs are present? Okay, and again, it turns out that there really isn't. But let's suppose that there are n inputs and m outputs. Okay, m now, again, it could be n choose 2, or about n squared over 2, or it could be much less. One thing we could do is just ignore the fact that we don't need all pairs as outputs and just pretend we do. Okay, and then we have the solution to the all pairs problem. Again, if we take the optimal algorithm that I didn't tell you about, what you'll get is R is n over Q, and it doesn't depend on m. M can be as high as n squared over 2. It doesn't matter. Okay. Well, there's another obvious approach which does depend on m, where you create one reduce that will receive only the two outputs associated, only the two inputs associated with that output. So that, hey, we only need Q equals 2, right? Because each reducer gets two particular inputs, and the replication rate I claim is 2m over n. Why? Because there are m edges. Each edge requires two inputs, so that's 2m inputs or copies of inputs that get shipped, and the replication rate is the average per input, so I divide by n, and so I get 2m over n. Forget about the factor 2, just call it m over n. So you've got either n over q or m over n. Those are the two obvious algorithms. Well, it turns out that, again, there's no general algorithm, something that will work for any n, m, and q, that's any better, because for any values of n and m and q, you can find a particular instance of a sum pairs problem where the replication rate that's required is close to the smaller of m over n and n over q. Those are the replication rates for the two obvious algorithms I just told you about. Okay. Well, here's the formal statement of it. It says for any epsilon greater than 0, you've got to have R is at least the smaller of epsilon times m over n. That's using the second algorithm, or the cost of the first algorithm, n over q, raised to the power 1 minus epsilon. Okay. So it says that there's no real daylight between what you actually need in some cases and those two obvious algorithms. Okay, and now again, remember, these are general. This is for general purpose algorithms. If you take any particular instance of a sum pairs problem, like, for example, the Hamming distance 1 problem, there's every reason to believe you might get something that's better than this minimum. Okay, so what do I want to say? Okay, we know MapReduce is an important way to do failure-resistant parallel computation. I think that there is a theory now for how good MapReduce algorithms can be. Obviously, it's sort of at the stage of we know that sorting takes n log n and pretty much nothing else. Okay, the theory, whereas let's say the theory for sequential algorithms was just really running time, here it's a trade-off between the reducer side, how much work each reducer gets to do, and the amount of communication you need. That's the real limit, the limiting factor in how good MapReduce algorithms can be. And let me just say that I invite anybody who wishes to think about applications of this theory, to sort of tell you how much we haven't done. Even the Hamming distance 2 problem, that is, the inputs again are bit strings of length b, and the outputs are all pairs that are at Hamming distance 2. There's different exactly 2 bits. We don't know what the trade-off between reducer size and replication rate is there. Okay. Question?
Can you apply the same theory on systems like Spark and Flink as well, or does it need to be modified for those systems?
Well, Spark, I guess both of them, in fact, that they have some other operators.
Exactly.
Right. But there's a finite set of operators in each case.
Yeah.
So in principle, you could develop a theory it becomes okay. Here it's a little bit more complicated. You may not have noticed this, but the theory is only the theory of one MapReduce step. Okay. Now you can I think you could do a theory for other operations besides map and reduce.
I mean, in general,
But
it's a directed data flow graph of operators.
yeah, but I mean, we tried to do this. Develop even a theory for a cascade of 2 MapReduce operations, and we come up with that we have one result in that area, and that is that a cascade of 2 MapReduce jobs can be made to have significantly less communication than one MapReduce job for the problem of matrix multiplication. That's as far as we've gotten. Okay. So I would say to look at other essentially to develop a similar theory for other operations like map and reduce, map feeding reduce. Yeah, you might be able to do that. But even a network as complicated as map feeding reduce feeding another reduce, we've had a lot of trouble with that one. Okay. Yeah, but please, by all means, think about these things. I think they're both interesting and important. Okay, so I have about 45 minutes left. I'm not sure I can go through everything I wanted to say about clustering, but let me say what I can. Okay, what I plan to do was just talk about the problem of clustering, really the 2 major approaches to clustering, which are called hierarchical and agglomerative. And then I wanted to talk about 2 big data algorithms, which maybe I'll get to one. They're both in the book. Let's just see how I can do. Okay, so what is clustering? You're given a set of points. You're given a distance measure between points, and you want to partition those points into clusters, possibly with some outliers that don't belong to a cluster. So that intuitively, the members of one cluster have small distances between them, and if points that are in different clusters have high distances. They're far apart. So here's, this is what you hope clustering looks like. Okay, you've got points in some space, and there are a lot of points that are nearby, and they form a cluster, and another points that are near to each other but far from the other points, and they form a cluster, and maybe there are a couple of outliers that don't really belong to any cluster. Okay. Well, I mean, if that's all that the clustering is about, you just eyeball it, right? Okay, in two dimensions, I think it looks easy. If you don't have too many points, enough that you can actually draw them on a plane rather than having to deal with them sitting out there in some database, you might be okay. And that's probably true. Okay. The trouble is, many of the interesting applications these days are not two-dimensional or three-dimensional, but they have some very large number of dimensions. And there's something called the curse of dimensionality. Now, I've heard all sorts of definitions. We know it's a curse, and we know what it does is it makes high-dimensional clustering very hard. And the way I like to look at it, again, it's not the only way you can look at it, is that in a high-dimensional space, all points are the same distance apart. Okay, so just to get specific, let's talk about an n-dimensional unit cube. Okay, all the points have locations between 0 and 1 in each dimension. I won't say how many dimensions there are. If they're two dimensions, you put random points into just a unit square. Well, they might be very close, have distance 0, or they could be opposite corners. It's very rare that they'll really be opposite corners, but they would have distance square root of 2, about 1.41. And if you take two random points in a unit square, you get a pretty decent dispersion of distances. Obviously, they'll be biased toward the low end. That is, you put one point down, it's probably somewhere in the middle, so there are more points that are close by than are far away. Now look at a 10,000 dimensional cube. Well, don't look at it. You can't see it. But if I put two random points down in any dimension, the distribution of distances will be a triangle. Okay, I don't know if that's obvious, but again, you put a point down. The probability, it can be any, as you expand the distance around it. For a while, you've got, you're expanding it toward the sides of the cube, so you get sort of double chance of finding the point there. At some point, you hit one wall, and now that chance goes down. So what it amounts to is the probability of having distance d decreases linearly in d between 0 and 1. Okay, now the distance between the points then is going to be the sum of the squares of the square root of the sum of the squares of 10,000 random variables, each one distributed like this. Well, what does the law of large numbers tell you? Okay. What it says is you take any distribution, could be the triangle, could be Gaussian, could be Poisson, anything. If you take a large enough number of random variables distributed that way and sum them, what you get is a Gaussian. Okay. And and by the way, the variance of the Gaussian is going to be linear, is going to grow linearly in the number of variables you take, in this case the number of dimensions. And therefore, the standard deviation is going to be the square root of the number of dimensions. So that says as the number of dimensions grows, the distribution of distances, it peaks at the median and gets narrower and narrower. So that says take any 2 points in a 10,000 dimensional unit cube, they are more or less the same distance apart. Okay, so what this is just, if clustering says I want to group the points that are close and separate the points that are far, it just doesn't mean anything. Okay. Now, in some cases, some data sets are not random, and therefore you might be able to extract something, but it becomes very hard to really, have to deal with the fact that all your points are going to be about the same distance apart. So, anyway, we'll do what we can. There's another problem, and I started off assuming that points live in a space. Okay, and so in fact I said, well, let's imagine the points are in this 10,000 dimensional unit cube. That means there are 10,000 dimensions. Each point has a position in the space. And then I even said, well, the distance will be the square root of the sum of the squares of the distances in each dimension. Yeah. Well, that's fine. There are other distances you can use. I'm not even going to get involved in that. But here's the problem. A lot of interesting clustering problems don't involve points in a Euclidean space or anything that looks like it. That is, there are a lot of interesting clustering problems where the points have a distance measure, and usually it means it satisfies the triangle inequality. I mean, all distance measures have to satisfy the triangle inequality, which says the distance between 2 points, x and y, is never greater than the sum of the distances from x to some z, and then z to that y. Okay. But the trouble is, in a non-Euclidean space, you've got a distance measure, but you don't have any place in the space. Okay. And I want to talk about two examples, Jacquard distance and edit distance. We know about Jacquard similarity now, right? That was the min hashing thing. Well, Jacquard distance is just 1 minus Jacquard similarity. Okay. Edit distance you may know about, well, it's the number of, you take 2 character strings, the number of inserts and deletes you need to make them equal. To make them equal, to turn one into the other. Okay, so, for example, you could represent a document by the set of words that appear in the document. And you might think that if documents have similar sets of words, they're about the same topic. You can define the distance between 2 documents to be the Jacquard distance of this set of words, whereas I said the Jacquard distance is 1 minus the Jacquard similarity. This, by the way, is not a really good idea. There's a better distance, which I don't want to talk about, called cosine distance, that is better for measuring distance of documents as sets of words. You probably also want to ignore the stop words because they don't really tell you anything about the topic of the document. But at any rate, the point is, people do want to cluster documents. There are several natural distance measures, and they're not Euclidean. That is, documents don't live in a space. They just have a distance to other documents. Another example would be, let's say, DNA sequences, which are sequences of these 4 characters, CATG. And you could define the distance between two sequences of these characters to be the number of inserts and deletes you need to turn one into the other. In the case of these biological applications, you often want to have certain other operations that are low cost. For example, taking a segment out of one string, reversing it and putting it back it's an easy thing for chromosomes to do. So you might want to make that give that a small distance. But anyway, again, the point is, given any two sequences, I can compute their edit distance. But the sequences don't live in any particular place. You can't say where a sequence is in a space. Okay, and again, this makes a difference. So we want to talk about clustering again. So as I said, one approach is called hierarchical, and this actually is probably the preferred method if your clusters don't have a regular shape. That is, if you remember my first two-dimensional example, the clusters were sort of ellipses. If that's the case, you want to use the second method, which is called point assignment. But if the clusters are weird-shaped things, then this is probably the best way to cluster. By the way, it's computationally more expensive, but it's more likely to give you a sensible answer. So the idea behind hierarchical clustering is you initially assume each point is a cluster by itself, and then you reduce the number of clusters by finding the two clusters that are nearest in some sense, and we'll talk about all of the many senses in which two clusters could be nearest. And you combine them into one, and then you repeat. At some point, you've smashed things down into as few clusters as makes sense, and so you don't want to continue any further. But that's a judgment call. Okay. The other approach is point assignment, where you sort of decide in advance roughly where the clusters are, maybe by sampling your data and doing some sort of an enumeration to find the best clusters. So that you have sort of an idea of how many clusters there are and roughly where they are, and then you just assign all the points in your space to the nearest cluster. Okay. Well, we'll talk about that later. Let's talk about hierarchical clustering. Now, there are at least two things I have to worry about. First of all, what's my definition of the nearness of clusters? Okay, and there. See, here's part of the problem here is there have been hundreds and hundreds of papers about clustering written, and they each have a slightly different idea of an answer to, for example, what makes clusters near. And sometimes you can even find a data set where that makes sense. Okay. So I think entirely too much has been said about these issues. But again, I do have to admit that there are different data sets. The clustering will work better when depending upon how you define distance, how you define nearness, how you decide when to stop agglomerating clusters. All of these things are choices that sort of make this an art rather than a science, and there's nothing much we're going to do about that. Anyway, so you want to know, how do you decide nearness? And sort of a related question then is, how would you represent the cluster of more than one point? Okay. Ideally, I don't represent it by the entire set of points, but I might have to. And Okay, so let's say, okay, again, I start off with every cluster every point is its own cluster. So at least in the Euclidean case, then you know exactly where each cluster is. Now, as you combine points into clusters, where is the cluster in the space? Assuming that there is a space that has so that you can answer the question, where is it? Okay. Well, again, in the Euclidean case, there's sort of a standard answer. It's the centroid, it's the average of the point. Okay, and if that's the case, then it generally makes sense to measure the distance between two clusters as the distance between the centroids of the clusters. Okay, now, again, there are other ways to do it. You know, for example, you might measure the distance between two clusters as the shortest distance between 2 points, one from each cluster. That sort of says, you know, they may be far apart on average, but they're sort of extending toward each other, so why don't we just merge them into one? Again, in some applications, that probably makes sense. It's more expensive than representing a cluster by the centroid, because now you have to look at each pair of points rather than just looking at the centroids of the two clusters. Okay, so here's a quick example, and it's a Euclidean example. There are two pairs of points that are distance square root of 2. Here's one of them. I break ties arbitrarily. Their centroid is, of course, right in the middle. Here now, the nearest two centroids of clusters are these two, which are still only 1 point. They're now replaced by their centroid. Now, I have really 4 centroids left. I have this one, which is just 1 point. I have this, and that. It turns out these two are the closest. So I combine them, and the centroid, notice the centroid will be twice as close to this guy as that guy because he represents 2 points, and he represents only 1. Okay. Well, then let's see. Then I've got this centroid, this, and that. It's these two that are next, so they get combined, and there's their centroid. I could combine the 2 remaining clusters, but now I've only got 1 cluster that really isn't terribly interesting. Okay. At any rate, this is how the 6 points represented by the O's. This is how you'd cluster them in a Euclidean hierarchical clustering. Okay. Now, what about a non-Euclidean clustering? See, again, the problem is, again, we don't have arbitrary locations. We do know, however, the points in the cluster. And we can use those points as locations, but what we can't do is average 2 points. That's if I take 2, genetic sequences, there's no notion of their average, the way there is if I take 2 points in a, say, 10-dimensional space. There is an obvious notion of average. So one thing you can do is you can represent a cluster in a non-Euclidean space by what's called the clustroid. And, well, again, the clustroid has itself, there are many definitions, but you might, for one possibility I put up here is that it's the point that is closest to the other points. That is, whose maximum distance to another point in the cluster is a minimum. Okay. Now, you can use the clustroid as if it were the centroid. That is, you represent a cluster in a non-Euclidean space by the clustroid and how many points does it represent. Okay. Well, here, okay. So one way you could define closest point would be it's the smallest minimum of the maximum, the minimum maximum distance, minimum average distance to the other points, not necessarily. Minimum sum of squares of distances, and you can come up with any number of other definitions of what closest means. Here's a simple example where fortunately it doesn't matter what I mean by closest. It's obvious that of these 3 points in a cluster, this point is closest, has the minimum maximum distance of any sort to the other 2 points. So this is going to be the clusteroid, and this guy will be the clusteroid of these 3. And therefore the intercluster distance, the distance between these 2 clusters, will be whatever the distance between this point and that point is. And that's all there is to it. Well, as I said, another way you could define the intercluster distance without having a Euclidean space is to look at the minimum distance between any pair of points, one chosen from each cluster. Again, that's more expensive than representing clusters by clusteroids, because now if you've got 100 points in one cluster and 1,000 points in another cluster, you've got 100,000 comparisons that need to be made. But it does have the advantage that it tends then to group clusters that are almost touching in some sense. A completely different approach is you want to talk about a notion of cohesion. And again, cohesion itself has many different definitions, or things that might make sense in certain contexts. But so here's one example. We can say the cohesion of clusters of a cluster is the maximum distance from the clusteroid. In other words, if let's say the clusteroid is the node of or point of minimum maximum distance, the cohesion is that maximum distance. Okay, and so the idea is you want to say, in this case, a small value for cohesion says that the points are really close together. Okay, and in the cohesion-based approach, you don't worry about the locations of the 2 clusters. What you say is, if I were to merge them, would they be cohesive or not? And then the winning pair of clusters to merge are those that give you the most cohesive cluster. Okay, and then you don't really worry about what was the distance between the 2 clusters. Okay, so again, definition of cohesion. One thing you might use is the diameter of the cluster. That is the maximum distance between any 2 points in the cluster. I mean, if that's small, that sort of suggests that these points are somehow occupying a small amount of space in the space that doesn't have locations. I mean, it technically makes no sense, but intuitively it does. Similarly, you could define it to be the average distance between points or clusters, or the density of the cluster. That is, so you might take some measure of distance, like the diameter or the average distance, and divide that by the number of points, or divide it by the square root of the number of points, or some other power of the number of points. Again, so there are all sorts of things you could do to define the cohesion. And again, depending on your data set, one definition might be better than another. Okay, so that's sort of all I wanted to say about the hierarchical approach. Let me see if I can talk very quickly about the point assignment approach. K-means, again, is the most popular of these approaches. Now, I'm going to describe something that assumes a Euclidean space. K is the number of clusters, and so one assumption is that I know how many clusters there actually are. And all I have to do is assign each of my points to the proper cluster. Okay.
But if you don't know,
Then you have to figure it out. And I'm going to actually talk about, I'll talk about that. You can use a binary search. It's not like I'll try k equals 2, then k equals 3, then 4 and 5 and so on.
there must be a measure of goodness then.
Yes. And I'll try that. Actually, again, in the Euclidean case at least, it does make sense that you can figure out what k should be, and I'm going to go to that. Okay, but anyway, you start by picking k, and how you do that we'll talk about later. We're going to initialize the clusters to have 1 point per cluster, and one approach is, well, if you don't have too many points, you could just pick a point at random, then pick the point that's furthest away from that, and then pick a third point to be the one that's whose minimum distance to the other 2 points is as large as possible. And then a fourth point such that the minimum distances to the other 3 points are as far as possible, and so on. So what you're doing is you're going to get k points that are as mutually far away as you can. And the idea would be that these probably belong to different clusters, and since you somehow know that there are k clusters, there must be k different clusters. There must be one representative from each cluster. Well, 2 problems. One is there might be outliers, points that really just don't belong to any cluster, and this scheme is going to get you the outliers. So what you're going to start with points that aren't really part of any cluster at all. So getting rid of outliers could be a problem. But there's also another problem is if the number of points themselves is 1 billion, you don't want to look at all billion points to decide which one is furthest away from the randomly chosen point. So that's okay. You pick a sample. You hope you'll have at least 1 point from each cluster. But if there are outliers, then even if there's a small number of points, you're probably better off sampling the points and then clustering them by any means so that even outliers will be noticed even in the small sample, and you'll find the k real clusters. Then you got to populate the clusters, and that's sort of it's sort of easy at first. You know where you know where the centroid of each cluster is. It's at the k sample points, the k points that you've selected as the initial seeds of the clusters. And you just look at each point and you put it in the cluster to which it is nearer, such that it is nearest to the centroid of that cluster. And then, by the way, you want to move the centroid of the cluster a little bit to account for the new point that you've just added. So then after you've assigned the points, you now have the true centroids of all k clusters. One of the interesting things is occasionally, if you now reassign the points, leaving those the centroids fixed, you get a different assignment. And I'm just going to show you an example in a second. So you can then reassign the points to the closest centroid, leaving the centroids fixed. So here's an example. I picked these 2 points are my initial seeds representing the 2 clusters. Third point comes in is closest to 1. Now, notice, because I've assigned 3 to this cluster, its centroid is now moved to here. Okay. Now, another point 4 comes in. That obviously belongs to this cluster. Its centroid is now moved to here. 5 comes in. Obviously belongs to this cluster. The centroid now is somewhere around here. And 6 comes in, the centroid's around there. 7 comes in, again, the centroid is here. 8 comes in, it's closer to the centroid here than to that centroid. So, well, these would be the initial clusters. Okay, and now these two x's represent the centroids, and that's it. They're not going to change anymore. But now I can reassign the points. And the interesting thing is that, well, it may not look it in this slide, but I'm going to tell you that this 1 is actually now closer to this centroid than to that centroid. That can happen. So if I reassign the points, the clusters that I get are actually this. And that sort of looks, could be, it's somewhat plausible. Okay. Okay, so now let me just talk about this matter of how you get things right. You don't know K.
So just in the other algorithm, when do you terminate?
Oh, you mean?
Does it converge?
Well, yeah, because I'm not going to move the centroids anymore. I'm going to leave the centroids fixed. Oh, okay. I could do the assignment again, and that might move the centroids a little bit. I could do it a third. If I wanted to, I could do that. But that's.
But would it converge? I mean, or will it just you can give
I don't know. It might not. It might not even converge.
Yeah, because yeah.
But I don't think anybody really wants to do it that many times. Okay, but at any rate. What I claim is, if you look at, I mean, you can pick K, do what I just said, and you're going to get some clusters. Okay, it could be the wrong K, and the clusters are silly, but you don't really know that again. With if it's a big data problem, all you have is the assignment of points to clusters, and you don't know what it looks like, whether it's silly or not. But you can try this for a sequence of values of K. You can use binary search, so you don't actually have to redo the same clustering for every value of K. But let's look at, the x-axis is the value of K, and the y-axis with the average distance of points to the centroid to which they are assigned. Okay, and obviously this should be a decreasing, the average distance should be a decreasing function of the number of clusters. As the more clusters you use, the more likely a point is to be close to some centroid.
Yes, it's like every point is a cluster, so it's 0.
Yeah. Okay, so now, if this were just some plain old decreasing function, who would know? But what I claim is there's going to be a bend in the function. That is, it's going to go down steeply until you hit the right K, and then it will still decrease, but not by much. And so I'll just show you in a couple of pictures. Remember, this is the example that I started with, and there really are 3 clusters. Suppose I try K equals 2. Well, the best thing I can do will probably combine at least 2 of those clusters into 1. So what's going to happen is, for the cluster that really should be 2 clusters, the centroid is going to be somewhere in the middle, and it's going to be far from all the points in the cluster. Okay. In this case, this cluster is sort of right. It'll have a relatively small distance to centroid. When I use the right number of clusters, well, still, since the outliers get assigned to a cluster, they will have long distances, but that most of the points will be relatively close to their cluster centroid. Okay. So there'll be a big drop going from 2 to 3. Now, what if I went to 4? Well, I might get something like this, where one true cluster got sort of arbitrarily broken into two clusters. That will lower the average distance within these two clusters a little bit, but not by much, because they're all the points are kind of close together anyway. Okay, so that's what I said. So the drop from 2 to 3 will be much greater than the drop from 3 to 4. And that suggests that 3 is the right number. And you don't have to have this nice two-dimensional picture to see that. Okay, so that's the answer to Seth's question.
Sorry, but that sort of assumes that even with the 4 or 3, you are more or less on the right clusters. Because in this two-dimensional case, probably it's easy. If you go for some more complex, you might not be sort of...
Yeah, right.
So
If you're not getting the right clusters anyway, then what does it matter? I see, seriously, you have to assume that you're getting reasonable clusters. And admittedly, that is an assumption. Okay. But if you're not getting reasonable clusters, you're doomed. Right. I'm sorry.
So about this bend that you said in the
Yeah.
graph that we see, so can we argue that if you see multiple of such sudden changes, it means that the structure of our data might have hierarchical clusters of different granularities?
Yeah, okay, that's interesting. In other words, it goes down steeply, then for a while it's sort of the same. And then drops. Well, see, I don't think that would happen, because at least if the algorithm is effective, it's going to, for the next larger k, it'll split two clusters into two natural subclusters. So things will go down. And then when you increase k by one more, it'll split another cluster. So things will go down a little bit more. So the things will really go down more or less linearly. If what you really have are big clusters, and each big cluster is a collection of little clusters. See, again, imagine that this cluster, it was coherent, but these guys really were closer. These were really tightly put together, and these were tightly put together. Then you really would have a pretty big jump in this, at least in this cluster. The distances would go. The average distance would go down quite a bit, because now you'd have two right centroids rather than one centroid, which was sort of good but not perfect for those guys. Okay. Well, okay, my time is almost up. Let's see what I can do. All right, let's talk a little bit about an algorithm called BFR, Bradley, Fayyad, and Reina. This is a version of k-means that's designed to deal with a number of points that are so large that they don't fit in main memory. Okay, so this is the big data aspect of this whole discussion. Okay, now they make fairly strong assumptions, which are first of all that the clusters are normally distributed in a Euclidean space, and the clusters are, I mean, the dimensions, they can have any number of dimensions, but the dimensions are independent. There's no correlation between the dimensions. That is, the clusters look sort of like ellipsoids, but not at an angle. They're rectilinear. They're along some they have a dimension along. Their long dimensions are along the axes. Okay, they're not necessarily spheres, but their axes are along the dimensions. Okay, so in the BFR algorithm, we're going to read the points one main memory full at a time. And the idea is that the points that have been processed so far are mostly summarized by some simple statistics. That is, we've decided where to handle most of the points from the previous memory loads. And we represent them by statistics. I'll tell you how that works. But you start off, again, you assume you know K, you know K, you start off finding initial centroids that belong to one to each of the clusters. How you do that, I'm not going to go into. You divide the points that you've seen so far into three classes. The discard set, which you hope is the vast majority of points, is there are things that are close enough to the centroid of their cluster that we're going to throw away the points themselves. Just remember that they belong to a cluster with a particular centroid. There's something called the compression set, which is groups of points that are summarized, but we haven't yet assigned them to a cluster. All we know is that they are nearby to each other. And then there's retained set, which are sort of things that look like outliers. We have no idea where they belong. They don't seem to look like any other points. So we just keep them as they are. Okay, so the discard set and compression set, they're both represented by statistics, sort of a centroid, and retained set, they're still individual points. So let's see, what are we going to do? To summarize either a discard set or a compression set, well, we need to know the number of points that are represented. There'll be a vector with one component in each dimension that is the sum of the coordinates of all the points in that set in the ith dimension. Okay. So it's not exactly an average, but it's the sum. And then we also want another vector that is the sum of the squares of the values in that dimension for all the members of this set. Okay, so if D is the number of dimensions, then you've got one value, the number of points, and then two vectors of length D. And that summarizes any set of points. Now, if I want the centroid, it's very easy. I just take the component of sum divided by n. If I want the variance, again, trust me, or trust the BF and R, I take the sum squared in that dimension divided by n, and I divide it by the sum divided by n, all squared. Okay, and then the standard deviation is just square root. Okay? So the way to think of it is that at any time, after you've processed some number of memory loads, you've got clusters, and it will have a centroid, which you can figure out. It's not immediate, but it's figured out from n, the sum vector and the sum squared vector. And all its points are discarded. It's just represented by those vectors and point. And then you've got maybe some number of compression sets. They're not assigned to a cluster, but they have been compressed because they're close enough. And then there are these points that don't belong anywhere yet. Okay. Okay, now a new memory load comes in. Okay, the first thing we're going to do is find those points that are sufficiently close, and I put quotes around it because I don't know what that means just yet, to one of the cluster centroids. You know where the cluster centroids are, and you just add those points to the cluster, and to the and they become part of the discard set. Okay, and by the way, you can add the points. You know how many points you're adding, so that tells you how much to add to n, the count of points. And then you've got the sum vector, so you just add these points to that sum vector, and then you take the squares of the coordinates of these points, and you add that to the sum squared vector. So that's how points get integrated into a cluster. Now, you then take, there are points that don't belong to, that haven't been assigned to a cluster. So the first thing you do is you take the retained set. Those are the points that look like outliers. You try to cluster them with the points that you don't know what to do with, and you hope that you'll find some of them are at least near enough that they can, that you can make compressed sets out of them. Okay. Well, I said this, okay, then you have to adjust the statistics of the clusters to incorporate the new points. And then you might think, well, you have these old compressed sets, and now maybe you've created some new compressed sets. You might want to at least merge them. Okay, and I'm not going to have time to talk about how you might merge them. And then, if this is the last round, you got to assign everything. So every compressed set gets thrown in with the nearest cluster, however far away it is, I don't care. And likewise, the retained points just get thrown into the nearest cluster. Well, again, the time is pretty much up. Let me just go very quickly through this. There are really two approaches to deciding whether a point's close enough to a cluster, and there are also some approaches to asking whether compressed sets need to be combined. Well, one way to decide whether how close is close enough to put a point into a cluster is what's called the Mahalanobis distance, and I'll define that in a sentence. And the other approach, which I'm not going to really talk about, is this. You know how many points are going to be assigned to a cluster roughly. So I take a look at a point. It may be very far from many clusters, but it may be a little closer to one cluster than another, than all the others. Now, if you've already assigned lots and lots of points, maybe half the points, you know that the cluster centroids aren't going to move very far, and you can statistically determine what is the likelihood of that cluster centroid moving by some distance d. If it is very unlikely that even if it moves the furthest distance away from this point, and the other clusters move the furthest distance they can move toward that point, this point's still going to be closer to that guy than any of the other guys. You might as well throw it into that cluster, because that's where it's going to wind up anyway. Okay, so that's another approach, which I'm not going to say more about. Anyway, the Mahalanobis distance is normalized Euclidean distance. That is, if the point, let's say it's k dimensions, so you have point x1 through xk. The centroid is c1 through ck. The first thing you want to do is normalize the distance in each dimension, which means you take the distance between the point and the centroid in that dimension and divide it by the standard deviation in that dimension. And again, you can compute the standard deviation from the sum and the sum squared in that component. And then you take the sum of the squares of the normalized dimensions and take the square root, and that is the normalized Euclidean distance, or the Mahalanobis distance of the 2 points. Turns out that if these clusters are normally distributed, and they are assumed to be, that's part of the assumption of the algorithm, then one standard deviation of Mahalanobis distance will be square root of d, the number of dimensions, which I guess was k on the previous slide. Okay, so you might say, well, I'm going to put a point into the nearest cluster as long as its Mahalanobis distance isn't more than 4 square roots of the number of dimensions, 4 standard deviations. So again, this is just a picture of what Mahalanobis distance might look like. You have one ellipse representing a single standard deviation, and then sort of something that's double size in each dimension, representing 2 standard deviations, and there's a bigger thing representing 3 standard deviations. So, so in each dimension, a standard deviation is fixed, but they can be, the standard deviations can be different in different dimensions, as I've suggested here. Well, again, whether you should combine 2 subclusters, lots of you could, for example, compute the variance or using sum squared and sum, calculate the variance of the points in the subcluster, and using a cohesion-based approach, say if I were to merge these two, would the variance be sufficiently small? Okay, so that's one way that they suggest to do it. And then there are a whole bunch of other ways, and I haven't even listed them here, but you can imagine different ways to decide, should I merge 2 members of the compressed set? Okay, so this is probably a good point for me to stop. The cure algorithm is interesting. It's in the book. It's not that hard to understand. So I'm going to just break here. I'll be happy to answer questions.
Thank you very much.
Any questions or advice?
Advice. Talk about something else next time.
Any other issues? Yes.
Yeah, I guess I could have a question about the curse of dimensionality, and you take like the k-means, and then the actual selection of features or dimensions as you have become more and more important, because if you add many dimensions, then the distance, as you say, mean nothing.
Yeah. Yes. Right. The k-means will only make sense if there really are, closely connected clusters, which there can be. Again, there won't be if you pick your points at random, I assure you.
Is there a way, assume we have like nice numerical features that we can add as dimensions. It's still, sometimes you have a clustering problem for a purpose. You have a certain idea. Let's say, from Spotify, so assume we want to cluster artists, and we can measure similarity between artists in different ways. But perhaps we want to do it for a certain purpose, like engagement of users or something. Some artists seem to engage users, they stream a lot from that artist. Is there a way to choose features that seems to actually create the clusters that we are looking for? Can we somehow evaluate if certain dimensions should be included?
You mean you want to decide what your answer should be and then design the features to get that answer? Yes.
Well,
yeah, you can do that.
If you want from the qualitative point of
Yeah,
view.
I mean, look. Okay, for example, height of the artist, probably not an interesting feature. Right. Again, without some understanding of the domain, I can't possibly answer how you would do that. I mean, I know it's important because you're going to get, in order for there to be clusters, you have to pick features for which there are significant that there are significant differences, and moreover, those differences mean something.
Because you can simply, from a more objective point of view, rather than having a subjective goal in mind, you can still evaluate the silhouette score or something for the clusters, and thereby see by adding and removing features you get higher or lower silhouette score and evaluation metrics. But is there something specific just for the number of features? That's really what I'm thinking of.
Well, I don't know. Well, one thing you can do. Let's say that we sit down and we come up with 10 features that you feel might distinguish artists. Okay, you might say, well, if I just put them in a 10-dimensional space, do the clustering, I will probably be cursed by dimensionality. So what you might do is say, all right, these are 10 dimensions, and I know the interesting analysis lies somewhere there, but I don't know where. So I'm going to just take 3 of the dimensions, and I'll cluster on 3 of them, and I'll see if I get anything interesting. And if not, I'll take another 3 dimensions. Maybe I'll try all sets of 3 out of 10. Or I'll start with 2. I'll just look at 2 dimensions, see if they, or even one. Just start with 1 dimension. Just see, do the artists cluster in any meaningful way in any 1 dimension, or any pair dimensions. Try to grow the set of dimensions that I use. But you really have to explore your features to see. Most of them are probably crap. Some of them mean something. Again, like, if you decided to find the height of each of your artists, that probably wouldn't be helpful. So you would discover that height, any set of, say, 3 dimensions that included height didn't give you anything very interesting. And therefore you'd say, well, height's obviously out from now on. And
I saw someone argue that they could basically take the cluster you have after the clusterings and apply a classification algorithm afterwards to just get the variable importance for trying to see what features actually best correlate to the clustering you have had, and in that way argue that we can limit the features to only the most important.
Yeah, well, that's what you probably want to do that. You want to figure out which. If you just don't know which features are important, that becomes your first job, is to figure out somehow which ones are important. And intuitively, when you do some clusterings with a small number of features, important features will be there when there are good clusterings, and not when they're bad. When they're bad clustering.
Probably, the height of the artist could potentially, distribute the artist in a very nice way, and potentially could be really good in clustering, even though they're useless. So, I argue that, this type of evaluation of which features should be included is really worthless. It doesn't work that way. But I could be wrong. Because it's really the only thing that, this variable importance will tell you is it's really good in separating artists. That's the only thing it tells you. But that's not the only metric you should have, I think, for evaluating, the features to include or not.
It's just so subjective. You might find, that there are tall artists and short artists, but they have all different kinds of music or paintings or whatever it is you think artists do. Yes, you got a good clustering, but it's not a useful clustering. It wasn't what you want, and so that has to be subjective, right? You have to.
There could be certain connection. For example, if you're for how much engaged they are with the audience, could be there's actually a correlation between height, because younger artists tend to be more social active online, engage more or something.
But then you can do dimensionality analysis by principal component.
Yeah. Yeah.
Principal component.
Try to
PC root.
get to the dimensionality reduction.
Exactly. But that if there is correlation between the features. Oh, great. So again, we're saying Jeff is going to leave us. He's going to jump tomorrow to the US. So we're saying Jeff
Yes,
one more time, and thank you for coming.
Thank you for having me.